Hello students, welcome back. Hope you are doing good. So, in this part of today's session, we will discuss about the kinetics. The kinetics of the gases with the help of your kinetic molecular theory. So, we will discuss about what are the different postulates. There are certain postulates of kinetic molecular theory. So, we will be discussing about those postulates. Next, we will discuss about the different velocities of the gas molecules. So, why to waste time? Let's start with this part. Kinetic molecular theory. So, you can see in this animation that you consider a container, and if you can see that there are gas molecules, right? These are the gas molecules, and these gas molecules always collide with the container. These gas molecules always collide with the container. You can see here that this is the wall of the container. This is the wall of the container. This is the wall of the container, right? So you have 6 walls. Since this is a cube, you have 6 walls. So in all the 6 walls, the gas molecules collide with the container, and they are not only collide with the container, they are colliding with themselves. So this is the region. This region is that region where my gas molecules are colliding with each other. So what can I say? My gas particles are not only colliding with the wall of the container, but they are colliding with themselves. So here also you can see that. Here also you can see the same thing, that the gas molecules are colliding with themselves. There are random collisions. One gas molecule can collide with any other gas molecules, right? Irrespective of the position, irrespective of the property of the other molecule, but a gas molecule, a single gas molecule can collide with any gas molecules. So what can I say? I can say now there will be certain laws. There are certain postulates I can say. So these postulates combine to give a theory which is kinetic molecular theory. So in this kinetic molecular theory, you will be learning about different postulates of your kinetic molecular theory of gases. So what are the different postulates? Gases consist of tiny particles of atoms, right? According to the kinetic molecular theory, gases consist of tiny particles. Those particles can be atoms, or those particles can be molecules as well. So next, the particles are so small compared with the distance between them that the volume of the individual particles can be assumed to be 0. This is a very important point you have to understand, that the volume of the individual gas particles or individual particles are very negligible. Their volume is considered to be 0. So the volume of the gas molecules is negligible, very less compared to the volume of the container in which it is filled in. Next important postulate. The particles are in a constant random motion. If I take the container, in that container the gas molecules are randomly moving. They are moving here and there, here and there, there and here, without any sequence or without any series. So they are just constantly moving in a random motion, and in that random motion, just in the before animation we have seen that they are colliding with the walls of the container, and there is collisions. These collisions lead to what? These collisions lead to pressure, right? So these collisions with the walls obviously leads to the pressure exerted by the gas. So this is another important postulates. Next important postulates. The particles are assumed not to attract or repel each other. So this is a very interesting point. That means when I see a container, so if there is a molecule here, this is a molecule here, there is a molecule here. So this molecule is hitting the wall, this molecule is hitting the wall. Remember, this molecule is not at all influenced by this molecule, and this is not influenced by this molecules. So what I want to say is that the particles are assumed not to attract each other and repel each other. The particles are assumed not to attract each other as well as repel each other. That means there are no intermolecular forces, either it attractive force or repulsive force. There are no force existing, there is no force existing between these gas particles. So the average energy of the gas particles is directly proportional to the temperature. This is a very important point. This is also another important point. When I talk about velocity, when I talk about random motion, obviously there exists a term kinetic energy, right? Or what is average kinetic energy? Suppose there are n molecules, the total kinetic energy by n is nothing but the average energy of the gas particles. So this average kinetic energy is directly proportional to the Kelvin temperature of the gas. So these are the few important postulates, and now what exactly kinetic molecular theory gives further information? It explains why gases are behaving, right? How gases are behaving, why gases behave as they do. So it deals very important. My kinetic molecular theory is applicable for only ideal gas particles, right? What are ideal gas particles? Ideal gas particles are those particles which obey ideal gas equation. So what are the conclusions? So the gas molecules, the ideal gas particles are so small that they are assumed to have zero volume. This is the first important conclusion from the postulate. The second is that they are in a straight line, right? They are moving in some random motion, and the motion is straight line. They are in a straight line motion, right? It's not like a given gas molecule. This is a wall of the container. This is the gas molecules. It is not moving like this. It is assumed to move like this. That means their motion is a straight line motion, not a other curved motion. So they experience elastic collisions. And what is elastic collision? In elastic collision, no energy is lost. So gas molecules or gas particles experience elastic collisions, and in which there is no energy is lost. And next important, the gas particles, they have no attractive or repulsive forces towards each other. I have already explained about this. That means there are no intermolecular forces. The intermolecular forces between one gas molecule and another gas molecule, or interatomic force between one atom and other atom, is zero. So the gas molecules, they have a kinetic energy, and their kinetic energy is proportional to the absolute temperature of the gas. So we can see how temperature plays a very important role in determining my kinetic energy. That means in determining my velocity. So as temperature increases, kinetic energy is increasing. So this is an important relationship. This is also one of the important relationship from your kinetic molecular theory. Now we will discuss about different velocities of the gas molecules. You know that gases have certain velocity, right? Because they have certain kinetic energy. That means gas molecules should have certain velocities. But the velocities of the gas molecules are defined in terms of three different velocities. One is the average velocity, one is the root mean square velocity, and one is the most probable velocity. So we will start with average velocity. So what is average velocity, students? Average velocity is nothing but, as per kinetic theory of gases, we know that each molecule is moving with different velocities, right? For example, there are n gas molecules. One gas molecule is moving with u1, another gas molecule is moving with u2, u3, and so on to un. So there are n molecules be present in the given mass of gas, each one moving with velocities v1, v2, and vn, and the average velocity will be what? It is the average of all the velocity terms. That means there are n velocity terms, and if I add them, and if I divide with n, it gives nothing but, it gives you an idea about the average velocity. So this value is nothing but the average velocity of the gas molecules. So this value of average gas velocity or average velocity is nothing but, this value turns out to be root RT by pi m, where T is the temperature, M is the molecular weight of a gas, P is the pressure, V is the volume, and again M is the molecular mass, and it is nothing but 8P by pi B. You will understand what is B when we discuss about the real gases. Next important velocity, root mean square velocity. So the name itself says that it is dealing with some root, right? So Maxwell proposed that this term URMS is nothing but square root of the means of the square of all such velocities. So what does that mean? It means that every gas molecule, if it has certain velocity u1, I can square it, right? u1 square, u2 square, u3 u square. So if I take the value of these averages, u1 square plus u2 square plus u3 square and so on to un square by n, right, I will get a velocity square. And if I take the square root of this velocity, I will get RMS. So it is the root of the mean, it is a root of the mean of the square of the velocities. So square root of the means of square of all such velocities. So you can see here that URMS is u1 square plus u2 square u3 square by n, or URMS is root 3 RT by m or root 3 PV by m. So next, so obviously if gases have certain velocity, they have certain kinetic energy, right? They have certain kinetic energy, because if there is a velocity, there is a kinetic energy. So as per the kinetic energy equation, you can have that my PV is nothing but 1 by 3 m into n into URMS square. That means for 1 mole n will be 1, so if n is 1, m into n will be what? Molecular mass. So I can write this as PV is nothing but 1 by 3 m URMS square. Why? Because this product of Mn will be capital M. So it will be what? Now I am multiplying numerator and denominator by 2. So it will be 2 by 3 into half m square by 2. So it will be 2 by 3. And what is half m URMS square? This is an important point. The role of URMS can be seen here. What? It shows that if I know URMS value, if I square it and if I multiply by mass and if I divide it by 2, this value is nothing but kinetic energy. So my kinetic energy of the gas molecule is proportional to the URMS square value or URMS value. So PV is nothing but 2 by 3 the kinetic energy of the gas molecule per mole. So kinetic energy per mole will be 3 by 2 RT. So you can see that kinetic energy per by a given molecule or kinetic energy per mole is depending only on the value of temperature. So kinetic energy of the given molecule, for example this is mole, right? Now if I just talk about a molecule, my kinetic energy per a given molecule will be 3 by 2 RT by n. What is n? N is the Avogadro number, and the ratio of your universal gas constant and your Avogadro number is your Boltzmann's constant. So it will be 3 by 2 kT, where k is the Boltzmann's constant and the value of k will be R by n. So you can see the importance, of your URMS, and you have developed now a relationship between your kinetic energy per mole with the help of temperature. So you can now in this slide you can also understand what is Boltzmann constant and how Boltzmann constant is used in determining your kinetic energy per a given molecule. So students, in this part we have taken two assumptions. What is the first assumption? The first assumption is that we are considering the volume of the gas molecules is negligible when compared to the volume of the container. This is the first assumption. The second assumption, we are neglecting the attractive forces between the gas molecules, right? So these are the two important postulates of your kinetic theory, and make sure you are feeding these 2 points into your core of your mind, because these points will be important when you define a real gas, right? So now you might have you might have getting some interest related to real gas, right? So I think you're excited, right? So no worry, right? In our next part, we'll discuss about the real gases itself. We'll discuss how a real gas deviates from your ideal gas, right? So till then, stay tuned, keep tuned to our sessions. Goodbye.